Okay, so it is a pleasure to introduce Susan Steele from University of Hawaii at Manoa. And his talk is on thermodynamic efficiency implies predictive inference. The floor is yours. Okay, you can start, Susan.
Yeah, okay, so I can hear actually nothing of what you just said, so it doesn't really help, and I can see very little in the video. Like, I just see masks, so I think it doesn't actually help me much to have the video. Can you turn your... I think you were right, you should probably turn your video bandwidth off for the bandwidth, you know. I thought it would help a little bit to see you guys, but I can't actually really see you. And also I can't hear you at all. So the audio we should try to fix, because if you want to ask a question, or if something isn't working, I should be able to see you. But also I would like to get some feedback from you as to like, what slide are you seeing right now? So to make sure that you're really seeing what I'm seeing. Are you seeing the title slide? Okay, are you seeing, whoopsies. Okay. Now are you seeing the first slide? Does it, now you see the first slide? So it says information processing, learning, and adaptation. Yeah? Is that what you're seeing? I just want to make sure you're seeing the right thing, because I've given a remote talk. Last time I gave a remote talk, the slides stalled halfway through the talk, and people were still looking at the same slide, and I was cranking on through it on my computer. So I want to avoid that. Okay? All right, so I'm curious about information processing, learning, and adaptation, and those are natural phenomena occurring in the physical world. So as a physicist, I want the physics-based theory for that. So this stuff is something that observers do, right? And much of physics has progressed by cutting the observer out of the picture. And many physicists are also uncomfortable with having the observer in the picture. I want to ask you one more thing. You see my little image here on the top, yeah, on the top right? Is it covering up the slide? Am I covering up the slide? Because on my view, I'm covering up the slide. Am I covering it up for you too? Okay. So, you know, while physical modeling definitely has led to some machine learning methods by modeling the brain and then coming up with neural networks, and to some degree also has led to an explanation of why they work, like random matrix theory, for example, there is still no real complete overarching theory that's based on physics. And machine learning does have some solid theoretical foundations, for example, in statistical learning theory. But this, like all areas of statistics, is based on purely mathematical arguments and not really based on physical arguments. And it also makes use of ad hoc measures instead. So what we want, or what I would like to see, is rather a physics-based approach in which complex behaviors can emerge from simple first principles, like we're used to in physics. And in particular, where the rules for how should we learn, how should we represent data, and how should we adapt to the world around us could be derived from those principles, instead of having to choose some objective functions ad hoc for a learning machine. Okay, this is the grand motivation. Are there any questions about that at this point? All right. So let me give you a brief problem description here. We have observers that can interact with their environment, so they sense, they process the information they receive, and then they act on it. And these things are often called agents. And so here's a little diagram. Oh, by the way, can you see my mouse, my cursor? This little arrow. So I'm pointing it to agent right now. Do you see that? Okay, that's great. Okay, so the the data in some sense is the currency that the environment gives the agent, and in some sense the agent doesn't really have access to the environment, only through the data, doesn't have any other access to it. So I don't know, if you want to become philosophical, you could ask whether the agent even has to assume that the environment is real, you know, like maybe it's enough to just see the data and all the reality lies in the data. And then there is also a currency that the agent exchanges with the environment, and those are the actions that the agent takes on the environment. Now, it's important to note, and this will become important later in the talk, that there are some generic restrictions on these agents. For example, they have to operate at finite times, and the world is only partially observable to them, typically. And they only have partial control over the world. Only in very special cases can they see everything and control everything. In the most general case, they only have partial access to the observables that they would like to know about their environment, and they only have partial control over those. No. Did this switch to the next slide? Yeah? Okay, so the models that people typically make of agents usually describe decision-making and behavior as some form of optimization. So what's being optimized there? It's often a utility function under some constraint of a cost. So there are many examples for this. For example, in reinforcement learning, the utility would be some form of reward or a discounted reward into the future. Decision theory works similarly. You have a loss or risk function there. And control theory, you also have some kind of error function. In game theory, you have a payoff matrix. And this is often traded off between, this utility is traded off between some cost. And the cost is often motivated by some philosophical arguments. For example, Occam's razor, you know, you shouldn't have an explanation that is too complicated, or by some statistical argument. So this cost measures in some sense the complexity or the capacity of the model class that you have. And the really big conceptual issue here is, how do you choose those? How do you choose your utility function and your cost function? You need to specify them in order to have your theory for your agents. And there are many reasonable ways in which you could measure these things. And so if there is no guiding principle, then you end up with a theory that's more descriptive modeling, right? I put this in and then I get these behaviors out, rather than having any kind of explanatory behavior or theory that tells you where these behaviors come from and what underlies them. Okay? Are there questions about this? Okay, so I want to take a different approach. So the approach I want to take here is I would like to first investigate the physical nature of information, then identify some fundamental limits to information processing, and then I want to postulate one simple principle and be able to derive the rules for learning strategies or even concrete learning methods, concrete algorithms from those simple principles. So that's the end of the grand motivation. If there are no questions about the grand motivation, then I'll proceed to the introduction. All right. What? All right. Okay, so let's look at the physical nature of information. So the thermodynamic origins of information go back to Maxwell. In 1867, the famous thought experiment emerged that was later dubbed Maxwell's demon, where Maxwell talked about a very observant and neat-fingered being. And I stole this nice drawing here from a guy named Norton. He's a philosopher, and he has copyright issues, so I asked him if I could do it, but he never really gave me a great answer, you know, so don't spread it too far. But isn't it a great drawing? Isn't that just the best Maxwell's demon that you have ever seen? What a cute demon! So for those of you who are not familiar with Maxwell's demon setup, the drawing here explains it. You have gas in a box, and there's this little neat-fingered being that's very observant and sees when the fast molecules come by and sorts them, right? So it sorts all the fast-moving molecules into the left part of the box, and it sorts the slow-moving molecules into the right part of the box, and thereby it creates a free energy difference. So people were saying, that Maxwell brought this up to discuss that the second law only holds, it's a statistical law, it only holds on average. And this little setup inspired many, including, most importantly, maybe Szilard. So in 1929, he outlined a simple physical foundation for information by giving a very simple daemon that doesn't require any sentient being to work. And we'll talk about that more later, but before we talk about that more, let's go on a little detour, because this work also inspired other people, including Claude Shannon, John von Neumann, and Wiener. And these guys studied, among other things, mathematical models of certain neurons and their connections. So people in the realm of Wiener, in particular McCulloch and Pitts. And so Pitts then came up with the first notion of neural networks. And this was refined over the years, but all the basic ideas are basically still in use. And this inspired then the first learning machine. I just had to show you this image because it's so fantastic. It's the perceptron. This is Rosenblatt. This is in 1957. And this perceptron then inspired a Russian mathematician to look into the mathematics of it and come up with the perceptron convergence theorem, which was the first proof that included the notion of a margin, and in that sense kind of inspired also other mathematicians to look into that, including Vladimir Vapnik, who came up with the most important insight that empirical inference, as implemented as a minimization of empirical error, is not consistent if you don't restrict the capacity of the model class, right? And so that then kind of dominated or has shaped our modern view of what machine learning is or what problem it solves. And we view it often as empirical inference with finite noisy data. So in the most ambitious version, empirical or inductive inference tries to solve the problem of going from empirical data to underlying laws. So the observer or several observers have experiences and they try to turn them into, they try to discover some laws of nature, hopefully, and then later they use those laws to give explanations for specific problems. And so in order to use our beloved deductive inference, we have to at some point as observers do this inductive inference step, right? Because we have to discover the laws. Now, just as a side note, machine learning often solves a simpler problem, which is to go straight from the finite data to the predictions, skipping the laws. But here you can see how this inductive inference, kind of the thing that machine learning studies, really does, in some sense, pertain to what observers do. And I'm saying that since observers are a part of the physical natural world, there should also be physical laws governing this process. So you can see how people could become uncomfortable with this, right? Because now I'm saying there should be laws governing the process that allows us to uncover the laws. Yeah? Okay, so any questions at this point? All right. So this brings us back to our central question, which is that the usefulness of a model and the cost of a model have to be weighed against each other, and there should be some natural physical laws from which the rules for inductive inference can be derived. So in simple words, how should an observer represent the data that he has or the experiences he has in physical memory? That problem should be answerable in the usual way. And so let's go back to step number 1 now. So let's go back to investigate this physical nature of information. So now we're back to the old guys, and we're going to try to actually skip over Maxwell and his daemon and take a shortcut. directly from Carnot to Szilard. I just had to put these imposing figures, Lord Kelvin and Clausius here, yeah, next to this young guy, Sadi Carnot, because even though he was already, he was older than them, right? I think he was already dead when they were active, but just, I don't know. I just like the way that they're looking at him. So Carnot's work was done before people had, oh, hang on, I have a problem with the Zoom here. Just a second. Before people had the notion of heat that we have now, so he was still operating under the assumption of caloric. Nonetheless, his work was very inspiring to all these people and actually inspired Clausius to come up with the notion of entropy. And so you probably all remember the Carnot process. So I want to review the Carnot process real quick because I want to use that review of the Carnot process to explain to you the Szilard engine, which is the basic information engine, which I then later want to extend. Okay? Now, if you are all super duper on top of the Carnot process, I can skip the next couple of slides. So can you let me know? Hello? Okay. Does any one of you guys have WhatsApp on your phone? Because you could just call me on my phone or on WhatsApp and that would work much better, you know, if this connection breaks again or something like that. Yes, but you would be able to tell me that the connection broke, right? Because I don't know. Okay, right now I can't get my video to work. Can you see me? Because I cannot see myself. Okay, now I can see myself again. Okay, great. So, do you guys want the Carnot process or do you want to skip it? Okay. So there are two steps in the Carnot process. One in which one section of it you do work on the medium, on the work medium. So here we have a gas in a container, and we started out at volume V. So like down here we have the full volume. That's where we started here. So we insert our piston here and push it to volume V1 at temperature T. So that's an isothermal transformation going from volume V to volume V1. Then we take the box out of the heat bath, that's at temperature T. So that's the blue stuff here is the heat bath, the cooler heat bath. We take it out, so we insulate it from that heat bath, and we push the piston in further until we get to some other volume V prime here. So that it then increases the temperature. And then we stick that container into a heat bath at the higher temperature to which we have raised it. And then we pull out the piston and decrease the volume from V prime to V2. at the higher temperature T prime. So that's again isothermal. This here is isentropic, the compression that increases the temperature. And finally, to get back to the starting state, we do another isentropic expansion back to the starting volume. So we change the temperature again from T prime to T. Okay? You say something if you have questions. Now we have to do the accounting for this process. So we can write down the work that we do during an isothermal compression of an ideal gas is just proportional to the logarithm of the volume change. And because the transformation is isothermal, the total energy change has to be 0, so the work has to equal the dissipated heat. Then during the isentropic compression, the work that we do on the system is this, and it cancels out exactly the work that we get out when we do the isentropic expansion again later on. Okay? So these two terms cancel, and there is no heat transferred, right? Because we've isolated the system. So the only terms that count in our accounting are these two terms here for the isothermal steps. So if we want to compute the total work out, then those are the only terms that we need to take into account. So what do we have here for the accounting? We have that the work we put in here is this, and the work we get out is this. So we use this convention that work going into the system, so work going into that gas is positive, comes with a positive sign. And work coming out of that gas, so work that we get out of that thing, comes with a negative sign. So then the total work out is that negative work coming out, right, the minus V prime, minus the work we had to put in, the W. And so that's this, if we just put these two terms together. Now notice that the adiabatic equation here, because we're doing these two isentropic transformations here, so the adiabatic equation implies that the ratios of these volumes have to be in a certain relationship. And so that then gives us that this factor here becomes the same. And so we have that the total work out is just this. Now, the Carnot efficiency is defined as the total work we get out of that thing divided by the heat that we suck in at the higher temperature. But the heat we suck in at the higher temperature is just the same as the work that we get out at the higher temperature. And so therefore the Carnot efficiency is just 1 minus the temperature ratio. So the low divided by the high temperature. And as you increase the high temperature more and more, the efficiency gets closer and closer to 1. Okay? So here is the summary of this Carnot process that I just talked to you about on the right-hand side. Yeah, this was the sketch we just talked through. And now I want to show you a complete equivalent sketch, but visually I like it better. So in the isothermal compression, I'm still going to use my piston here to move from V to V1. But in the isentropic steps, I am going to squeeze that box sideways so that my piston can stay in the same place. And I'm going to the same volume V prime, so I'm not doing anything else. Yeah, I've just made the engine a little bit more complicated because I've introduced another degree of freedom. I can squeeze the sides of the box. So I make the box smaller laterally here, like this. Later you'll see why I find this easier to think about. One reason is because visually it's just nicer, right? Because remember that everything was about these volume ratios. So now it's easier to parse the volume ratios, right? Okay, so now we go from this idealized heat engine straight to this idealized information engine. And how do we do it? Well, first of all, we replace our ideal gas with a one-particle gas. And then we take out a whole bunch of things. For example, we do not do this compression of the gas, this isothermal compression. Instead, we just insert a wall in the middle. Since we only have one gas particle, this means that the gas particle must be on either side of the wall. Then we skip the isentropic steps altogether. We don't do them at all. And therefore, we also don't end up at a higher temperature, right? So the whole thing stays at the same temperature. So this thing here is blue instead of red, okay? And when we do the isothermal expansion, we just expand. And so because we have put the divider into the middle, we've basically chosen that this volume V1 is V half. So when we do the isothermal expansion, we go from V half to V, which means that the work we get out is proportional to the log of 2, right? Because that was the volume ratio. Okay? Any questions about this? So look at the magic here. You don't do any work at all, you just slap your partition in, but you can get a little bit of work out. Holy schmoly, have you built a perpetual motion machine? Have you defied the second law of thermodynamics? Why not? Well, because you can only do this nice trick if you know which side of the partition that particle is on. But if you don't have that knowledge, you can't extract any work on average. So somehow you have to acquire and memorize that knowledge, and you have to memorize it for the time during which you do this isothermal expansion. Because if you can't remember it for that time, and you don't know, you go halfway and you say, oh, I don't know which way should I be going, this way or that way, oops. If you don't set it up in such a way that the memory sticks, then you can't do this trick either. And this was kind of Szilard's main point. For all of you who do speak German, I really recommend to you to read this Szilard paper, this 1929 paper, in the original text. It's a lot better than the English translations that are out there. Okay, so we need to know, is this particle here or there? So we need to measure and remember the particle location. And this step then must be dissipated. So how can you implement the step? So the idea is, so you need, you can't just have these 2 steps in your machine. You have to have at least a 3rd step. So that 3rd step is, you insert your wall, and then you measure and remember, is this thing on the left or is this thing on the right? And if it's on the right, the isothermal expansion goes this way, and if it's on the left, it goes the other way, and this way you get your work out. Now, one mind-bogglingly simple way to implement this here, right, in a physical system is to use yet another gas with a piston. So you have another 1 particle gas in a container, and you just compress it if the thing is on the left, and you compress it the other way if it's on the right. So this then becomes your memory. So you don't just have that work medium as part of your information engine, but also that memory that has to be physical too, somewhere in some way. You can also put a transistor here, or any bistable system. It doesn't matter. This is just for illustrative purposes. I've put another little gas box here. And then, of course, now you can close the cycle for the full engine, which has to include the memory. And this is often not explicitly listed. If you look at the papers, they often just describe this. They often have a drawing in there that's kind of like this. Yeah. So somehow the memory doesn't get so explicitly listed. But, everybody has pointed out that it is the deleting of the memory
Yes, we can hear you.
Very good.
Okay, so I have your
There-
slide.
which slide did you hear me talk? I don't know when it broke off.
So you can hear me?
I can hear you. Can you hear me?
Yes, yes. We will.
I'm asking you which slide. When did my connection break? I don't know when the Zoom connection broke. I don't know how long I was talking without you listening.
No, but no problem. So give me the. So we are in the slide on. We were on the slide on Szilard engine. Okay, you can comment your slide on you. Just give me the title of your slide, and I show the slide to the audience. Okay.
Just tell me, when did our connection break?
Just at Szilard engine. Non? C'était après? No. Close the cycle. Close the cycle. Start again at close the cycle.
Okay, very good. I'll try to hurry through this because we're running out of time big time. Okay, so we can now build like a cycle from two things, right? The work medium and the memory. And what we do is we insert a partition into the work medium. Then we make the memory by pushing that little piston in step 2. And that costs us work, and that's the WM there. So I am on slide number 27 now. Yeah?
So give me the title of
Hello?
give me the title of the slide. It's easier.
What you just said, close the cycle.
Close the cycle. Okay.
Yeah? Okay, so that the way that you should think about this large engine is that it contains not only one particle gas, but it also contains some way of capturing the memory. And like I said, that could be any bistable system, but it can be, for example, another one particle gas in a container. And then you see that the cycle goes like this. You insert the partition into your work medium in step 1. In step 2, you measure and remember where's this particle, and you do it here in my one particle gas memory. I do it by just pushing the piston in from the left if the particle is on the right, and from the right if the particle is on the left. And so then the position of the particle in my memory tells me about the position of the particle in the work medium, and that's how I can get the work back out. When I've gotten the work back out after I do the third step there, the isothermal expansion, then there's no correlation between the memory and the work medium left. And then I have to pull out the partition from the memory and stick it back into the work medium. So can you go to the next slide?
Okay. Szilard engine.
So you see that this is a useless machine in the sense that it gives you no net work out, right? The amount of work that you can get out and the amount of work you have to do for your memory making process are the same. So you get zero net work, but you get a method to convert work to information when you measure and remember something, and to convert information back into work. And it's that you are correlating the two systems with each other in step 2, and that costs energy. And in step 3, you're destroying these correlations and using them to extract energy again. And so if you look at the joint distribution of the random variable that describes your particle in your work medium and another random variable that describes your particle in your memory, then that joint distribution factorizes before you do anything, before you measure and remember. But afterwards, it doesn't factorize anymore. But then you use all of the correlations to get as much work out as possible. So afterwards, after step 3, it factorizes again. So this is indicated on the very right here, where I wrote out that joint distribution. Yeah? Are you with me?
Yes.
Okay. So that's how you can see that it's the mutual information between those two systems that controls how much work you can get out of this, but that also controls how much energy you dissipate when you run your memory. Okay?
Okay.
So this is something that is known. Many people have talked about this, starting with Szilard, definitely Landauer, and then many people recently. There's a nice review from 2015 by Carnot and others in Nature Physics, so this is nothing new. This has also been measured. If you can go to the next slide, we have here one experimental verification of this. And I don't want to go into the details, and it's not the only one. There are several out there by now. So go to the next slide. So now we're on the slide that says assumption in this discourse.
Okay.
Yeah? So this discourse, how can we convert information into work, and what are the ultimate limits? Well, I've just shown you the ultimate limit, right? For 1 bit, you need to do at least kT LNG joules of work, right? That's the ultimate limit. And you can get at most that much out if you have 1 bit of information. But to achieve those ultimate limits, some assumptions were being made. And these assumptions are being made in the context of these idealized systems, these idealized information engines. One assumption is that we can measure the quantity that we need to know about. Another assumption is that we can afford to move arbitrarily slowly, and that we have complete control over the system. And then, under these assumptions, we can actually achieve the ultimate information to work conversion limit. Now, I want to make the point that real-world learning systems, real observers, do not have those luxuries. They typically cannot measure everything that they need to know about an environment, and they run at finite times, and they have limited control. And so, therefore, we can ask whether there are tighter bounds than these ultimate limits, because these ultimate limits won't be achievable for real-world learning systems. And so I want to focus today on this partial observability and ask what's the tighter bound. So here's an example on the next slide, if you move to the next slide.
Okay.
Are you on the next slide? So you can create a simple example for a partially observable environment if you just tilt the box. So let's say you can move the partition up and down, but you're still looking from the bottom, so you're still looking at the position of the particle along the x-axis, as we were before. So this is a partially observable world, because a fully observable world, you would be able to see the x and y position of that particle. But here you're restricted to see only the x position. But unfortunately, you can move your partition only in y position. So you can't actually do anything with this. You can't extract any work, no matter how much information you capture about the x position of this particle. Yeah?
Okay.
Now, if you change the box a little bit by including forbidden regions, excluded regions, so here I've made those regions dark gray. So the particle now can only go in the white spaces, and the black line in the middle with a little arrow pointing up and down is still that partition that I can move to extract work, like in the original Szilard box. Yeah? Now, because I've made these forbidden regions, I have created correlations between the x and the y positions of this particle. So now, even though I can only observe the x position, I can make an inference about the y position, and I can extract some work. Okay?
Okay.
So I've chosen this example with these weirdly shaped, staircase forbidden regions just for convenience, because it's easy to eyeball what's going on there. But one way in which you can maybe get to this more naturally is if you just tilt your viewing angle on your original Szilard box. Then that would correspond to those inaccessible regions being just a straight line, so just triangles cut out of the box. Okay, so now go to the next slide. Now we can ask ourselves, how much work can we get out of this? So when we ask ourselves that, we note that a fully informative memory costs more on average than it can yield. So the best we can do here, the memory with which we can capture everything that we, as much as we would like to know, is a memory with 3 states. So it can be -1, 0, or 1. This M variable is my memory variable. Are you on the slide 33 that says how much work?
Yes, yes.
Okay. So this memory captures log 3 bits of information, and so therefore it costs at least KT log 3. But it can yield less than that, right? Because 2/3 of the time you get a -1 or a 1. So you know, oh, that particle must be down or must be up, so you can get your log 2 units of work out of there, right? But if the particle is measured to be in the middle, then you don't know whether it's up or down, and you can't do anything. So you get at most 2/3 KT-ln2 out. So overall, the dissipation is larger than 0. So this ultimate bound of 0 dissipation is unachievable. Next slide.
Okay.
Now we can say if the ultimate bound is unachievable, then we can ask if there's a tighter and maybe more meaningful bound on dissipation than just this 0. So equivalently, we're asking for a partially observable information engine subject to a tighter bound on dissipation than that pointed out by Szilard and by Landauer. And if so, could this tighter bound inform how observers ought to process information efficiently? So go to the next slide, please.
Okay.
So now I'm on slide 35, and the title is Bound on Dissipation.
Okay.
So the important insight here is that the observer can't turn all of the information that it gathered, so all of the information about this X position, into work. But instead, the observer has to make an inference about this Y position. And only the relevant information, namely the information that is kept in the memory about the Y position of the particle, can be turned into work. And this relevant information is indeed 2/3 ln2. So go to the next slide, please.
Okay.
The one thing you could ask is, you could say, well, maybe we can reach 0 dissipation if we use a different memory. Maybe we shouldn't use a 3-state memory. Maybe we should use a cheaper memory that costs us less. Lower the cost. Maybe we can have less dissipation. So let's use a 2-state memory. Indeed, that does cost you less, but it also gets less out. And the difference is still larger than 0. So you still cannot achieve 0 dissipation, this ultimate bound. And also in this case, you see that the amount that you can get out happens to be exactly the relevant information that your memory captures. And I've chosen this example for it to be so, and this is why I've chosen this weird staircase shape, and I've chosen it so that you can basically eyeball what is the information here, right? It's easy to calculate. But you can show this that this is true in general. So if you go to the next slide. The next slide is number 37, and it says general bound.
Okay.
We can show, in general, that for partially observable information engines, it's the relevant information that bounds the total yield, and it's a tighter bound than the total information. And the dissipation then overall is bound by a trade-off between how much memory do you capture overall and how much of that memory is relevant information. And for isothermal information engines, there's a simple interpretation that your dissipation is simply bound by the amount of relevant information, irrelevant information that you capture. So the more irrelevant information you decide to retain in your memory, the higher the dissipation has to be. So for generalized information engines, though, they can run the memory forming step at a different temperature than the work extraction step. So I want to give you an example of that in the next slide. So if we go to slide 38, the title is a Szilard Carnot process.
Okay.
So I have the same kind of box here with the excluded regions, and on the left side, I'm just running it isothermally with a 2-state memory, because if I run it isothermally, the 2-state memory is better than the 3-state memory. But on the right side, I'm reintroducing the isentropic step that we had in the beginning in the Carnot process. And now you see why I wanted to replace that Carnot process with the Carnot process where I squeeze the sides of the box during the isentropic step. Because now this becomes very simple here. But in the first, going on the right side of that drawing, where it says memorize 3 states, in the first step, I make my 3 states, I make my measurement, and I create my 3 states memory. So that's indicated by going from the left state there to the right state where there are these gray underlying boxes there for the 3 different possible outcomes that I can have in my memory. So now my memory is in some state. And this costs me at least on average kT log 3. And then when I cross this little dotted line with the arrow going down in the next step of the cycle, I'm doing this isentropic compression, and I'm doing it by squeezing the box from the side. Now I've isolated the box from the heat bath, I've increased the temperature to a higher temperature, and now I'm going to extract my work at the higher temperature. And so the work that I extract at the higher temperature is proportional to that higher temperature times the relevant information I have captured. And so if I now compare this 2-state memory, which has lower cost on the left-hand side, to the 3-state memory, which has a higher cost on the right-hand side, well, the 2-state memory has a lower amount of relevant information than the 3-state memory. The 3-state memory captures the maximum amount of relevant information. And so which memory is better simply depends on the ratio of the temperatures. That's this alpha parameter there, the high temperature divided by the low temperature. And you can calculate what the critical alpha is, from which on it is better for you to summarize your memory in 3 states, because then you have lower dissipation. So if you squeeze the box enough and you increase the temperature enough, then it pays off to keep a memory that has 3 states. Okay? So can you go to the next slide? So I have a friend of mine made some simulations of this, and you're going to have to take out this colon 8000 there, otherwise the movies don't run, and I guess you can look at them later because we don't have any time now. So I want to show you the general analysis and how to derive the general bound. So if we go to the next slide, I have, more historical things here, and I'm going to just skip over them because they're not important. I just want to mention that in the general analysis, I use a concept that comes up in Far From Equilibrium Thermodynamics, and go to the next slide, 41, that says core concept used here. The core concept I use is that of the fact that a non-equilibrium free energy can be associated with a non-equilibrium distribution. So this has taken a while to be accepted in the physics community, but by now there's again some experimental verification of these concepts that date back at least to the 80s, and people have been more accepting of it. So I just want to let you know that that's used in the general analysis that I'm going to be presenting. So when I talk about free energy, it's a generalized free energy. Let's go to the next slide now. So now we can finally look at this partially observable generalized information engine and do the accounting for it, like we did for the Carnot engine and for the Szilard engine. So are you on slide 42 that says partially observable generalized information engine?
Yes, yes.
So the notation is that we have some work medium, some system, this is our gas in the box that we want to get work out of. And the system state can be decomposed in one of 2 ways. Either I can describe the whole system state by all the things that I can observe and as everything else, or I can choose to describe that whole system state by all the controllables and everything else. So I'm changing the notation here from x, which before in my little example was just the x coordinate, and y, which was just the y coordinate of the particle. I'm changing it here to something more general, right? X are now the observables, and x bar would be all the random variables that are not observable. And together, they would, if you concatenate all these random variables together, you would get the full system state, which would be this v variable. And the same for the controllables, which are now called y. Okay? So it's important to keep that in mind. The memory is still going to be called M. It's It's constructed from the observables, and it's used to infer the controllables. And the free energy is, of course, the average energy minus kT times the entropy. And because I'm using generalized free entropy, the Shannon entropy appears here as the entropy. And I need to look at this free energy change, this delta S, of the joint system of the observer and the work medium together. So I need to take a look at the generalized free energy change of the joint probability distribution of the random variables Z and M. And when I write that out, that free energy change, it's again the average energy change, which with the first law is just the work done on the system plus the heat absorbed by the system minus kT times the entropy change. Now go to the next slide. So I need to do this accounting, and then I can use, are you at the next slide?
Yes, yes.
The next slide has the same title, but it says, in the first point, it says joint free energy change, delta F equals W plus Q minus KT delta H. I need to do this accounting for both steps, the memory making step and the work extraction step. And in my accounting, I can use the second law of thermodynamics, which tells me that the dissipation is non-negative on average. And this translates into the heat that is being produced in the memory-making step being no smaller than the negative entropy change. So the entropy decrease is compensated by a heat dissipation in the memory-making step. And in the work extraction step, the absorbed heat is compensated by an entropy increase. So now we need to just compute these entropy changes. And then I've given you a little bit of notation here. I'm using the usual kind of engineering notation for entropies and information, kind of the stuff that you would find in the cover Thomas book, elements of information theory. So for people who aren't familiar with that, I just wanted to show the notation so that they can follow. If that's all fine, then let's move on to the next slide. So in the next slide, that's slide 44, we are going to do this accounting. So we're going to look at this memory making step. Like I said, before the memory is being formed, there are no correlations between the system and the memory. And afterwards, they are correlated, but the memory depends only on the observable. And so the total entropy change then becomes proportional. This just becomes the negative information that you create. And so the negative of the total entropy change, which was the limit on the heat production, just becomes the mutual information that we capture. And this is, again, the known Landauer Szilard thing. Now, in the work extraction step, remember that we have these controllables Y that we can change and that we can decorrelate from and thereby extract work from the system. But we also have everything else that was this Y bar that we cannot change. And we've set up, because we want to reach the limits, we're going to set it up so that we leave no correlations left behind, right, left unexploited. So we exploit all of the correlations that we can exploit, and then the total entropy change just boils down to the information that we have in the memory about these controllable variables, about these relevant variables. So this is what I call the relevant information. So the absorbed heat then can be no more than the relevant information that we have captured in our memory. And this is new. And so let's go to the next slide. So together, these things then give you a new lower bound on dissipation, which is tighter than the ultimate limit. Because if you run this, are you on slide number 45, where it says lower bound on dissipation?
Yes.
Okay, so this slide repeats again what I just said in the previous slide, and then puts it together. And the equation or the inequality in the red box tells you that the total dissipation encountered by this generalized, partially observable information engine is controlled by a trade-off between how much memory do they capture at the lower temperature and how much of that memory is relevant information, which they can then turn into work at the higher temperature. Now, if you run an isothermal information engine, meaning that you don't change the temperature, so you're running the memory step and the work extraction step at the same temperature, then you can never expect to get any more than zero work out of this engine. In that case, this has a very simple interpretation, right? Because now you're just looking at a difference between the total memory minus that part of the memory that is relevant. And so that is the irrelevant information. So in isothermal engine, in isothermal partially observable information engines, which are a more general class than fully observable information engines, the dissipation is controlled by the irrelevant information that is captured in the memory. Now, please go to the next slide. Now we can see if we can use this to get from information engines to strategies for data representation and to some machine learning methods. So this is just a simple sketch of a simple information engine, and I just wanted to argue that that's a model for kind of like a very simple proto-agent because it can sense something and do something on the world. Let's go to the next slide, please, 47. So now I want to, I'm still following my steps where the first step was to look at the physical nature of information. The second step was to ask for the limits. And the third step now is to postulate a simple principle. And so now I'm going to postulate my simple principle for observers. I'm going to say that there is no reason for an observer to choose a priori a data representation strategy that will force the observer to dissipate more than it absolutely has to under all circumstances. So I want you to note that this is different from saying observers always minimize dissipation. I'm saying something that's much less strong. I'm saying, set up your mapping from experiences to memory up in such a way that you could, with your specific implementation in your specific environmental context, achieve the lowest possible dissipation if you needed to. But I'm not saying always do it, always achieve the lowest dissipation. I think that wouldn't make any sense because sometimes you want to dissipate, for example, because you want to make processes run one way, you want to make time go one way, or because you just have to do things fast, right? But I'm saying you should set up the structure of the mapping that relates your experiences to your memory in such a way that efficiency is possible. So can you go to the next slide, please? Slide 48.
Okay.
So this slide has the title Data Representation Strategy from Minimizing Lowest Achievable Dissipation. So my postulate is that an observer should minimize this lower bound on dissipation. So this lower bound on dissipation is given in the box there. It's the K times the lower temperature times the memory minus the higher temperature times the relevant information. And so we want to minimize this over all possible stochastic maps from data to memory because the memory is characterized by this stochastic map. And doing that is basically the same as solving what is known as the information bottleneck method problem, where this trade-off parameter between how much relevant information do you keep and how much total information do you keep now has a real concrete physical meaning. It's the ratio of these temperatures. It's the high temperature divided by the low temperature. And all the solutions to this optimization principle must satisfy the bottom equation in which you can see that a memory is chosen, when a data point is given, a memory is chosen with higher probability if the relative entropy, so the D there, the big D stands for relative entropy, the Kullback-Leibler divergence, between the first distribution there, this P of Y given X, that's essentially the data distribution, right? That's what is the distribution over the relevant quantities if the observables are given. And the second distribution there is basically the model distribution. That's what's the distribution over the relevant quantities when your memory is given. So you want to minimize the distance between these two distributions, meaning the memory gets chosen that makes those two distributions, for which those two distributions are closest together. Okay? Are there questions about that?
Not for the time being.
Okay. So now let's go to the next slide. Yeah. So we're getting close to the end. Let's go to the next slide.
Efficiency.
Yes, efficiency. So in this very physical context of partially observable information engines, we can ask for efficiency really in a Carnot sense. There are other definitions of efficiency floating around for information engines because, like I told you before, this is a large engine, really just converts between work and information, but it doesn't really produce any total work out. So that if the total work out is zero, then you can't define the Carnot efficiency because the total work out is zero. But here, we've created an engine that can produce total work out, so we are in a position where we can use the regular Carnot efficiency to measure efficiency. And so you see here that if you calculate the efficiency of these partially observable information engines, the Carnot efficiency gets reduced in proportion to the ratio of how much irrelevant information are you keeping compared to the relevant information that you're keeping. And that gets multiplied by the ratio of the temperature. So that's kind of interesting and neat. And this also tells you that this bottleneck method provides an observer with a strategy that allows the observer to achieve the largest efficiency possible when it needs to. So let's go to the next slide. The next slide says generalized information bottleneck framework. So I just want to mention in passing that this information bottleneck method can be extended into something that I call the generalized information bottleneck framework. So it can be extended into dynamical and interactive learning. It can be applied to reinforcement learning. It contains, as special cases, many other interesting models. And it can also be generalized to quantum information bottleneck. And finite data can be dealt with too. So the questions of complexity control. And go to the next slide, please. I also want to mention in passing that you can take this thermodynamic view to analyze what's going on in the Boltzmann machine, for example, because basically everywhere where information theoretic quantities show up in machine learning, you can take this physical view and ask what is really going on here. And so the Boltzmann machine basically minimizes a lower bound on the average dissipation that's encountered during predicting a new label, a new pattern. Go to the next slide, please. And I also wanted to mention in passing that you can use similar arguments to derive sort of core ingredients of information theory, such as Shannon's rate distortion curve and Shannon's channel capacity. So the rate distortion curve you can relate to a minimum effort principle, as you can find in Zipf's interesting book from the 20s. I don't know, most of you have probably heard of Zipf's law, right? Because that's a common thing that we know about if we study complex systems, yeah? But I don't know how many of you have actually read Zipf's book. It's a trip. It's a bit of a waste of time, but it's a trip. Anyway, so let's go to the next slide. So I want to conclude that what I want to convey to you today is that making a data representation that basically minimizes the smallest possible amount of dissipation in these generalized partially observable information engines requires the use of predictive inference in the sense that you keep only that part of the available information which is relevant to the task at hand. So in some sense that defines for you the predictive inference task, and it tells you how to solve it. And so this is concretely solved by this information bottleneck method, which you can derive from this rather mild postulate that I have given, which says that an observer has basically no reason to represent data in a way that forces the observer to dissipate more than he absolutely has to. Because that would just be stupid, right? The observer would just be like abusing its resources, wasting its resources, and why should it do that? So now we can go to the next slide, which is the outlook. We can then ask, do you have the next slide?
Yes,
54?
yes.
We can then ask, can we use the same reasoning maybe to find also other general learning strategies? So here I've shown you, if you want to be energetically efficient, then you have to do predictive inference. But maybe there are other strategies that we can find by a similar reasoning. So the general idea is that, observers use those rules that will allow them to come as close as possible to some physical limits on information processing, but will allow them to come close as possible whenever they need to. It doesn't force them to always be at the limit, And there are other important limitations on learners that I've already mentioned today, right? Those were partial control and finite time operation, for example. And then there's also other important physical limits on computation along other dimensions, right? For example, along the dimension of speed or accuracy or robustness or other things. So you could extend this treatment to explore those physical limits and ask whether they imply other different rules of information processing for observers. You could also extend the treatment away from averages. Always talked about today were average quantities, average work, average dissipation. But there is such a thing as single-shot thermodynamics, so you could think about what kind of learning algorithms can you derive if you extend this treatment to worst-case scenarios. Very good. So let's go to the last slide, which is my thanks slide.
Okay. Thank you, Suzanne. We are very late, but sorry for the technical problems.
I'm sorry too. That's terrible. This has never happened to me like this before.
Yes. So next time you will attend physically to the conference. One question in the audience. I have one. Is it your principle related also to minimum description length principle, for instance, or it's not related?
Yes, I think it is. I think that you can derive this minimum description length principle in a similar way in which you can, for example, derive this minimum information principle that you have in rate distortion theory or in the bottleneck. You should be able to also derive this minimum description length principle from a thermodynamic argument that runs very similar to what I've given you here. So it's been on my bucket list for a long time to do that, and I've told lots of my collaborators, including Matteo Marsili, and I think that he is slowly making progress in doing that. But I'm not sure he's there yet, and I haven't really looked at it. But I think, yes, those things are related. I think there must be some, more comprehensive and general theory that allows you to derive larger classes of these things that are very similar, right?
Okay, so thank you, Suzanne.
Thank you for having me there.
Thank you.
Even if it was just remotely, and I hope you're enjoying your time at the Houches.
Thank you.